Hello. Please confirm that you can see the presentation and hear me. Hello. One of you, please confirm that you can see the presentation and hear me.
Sir.
Yes, can you? Hello. Is there any issue?
No, sir, no issue. Yeah, it's visible.
Okay, okay. Thank you. So all of you can hear me and see the presentation. I shall begin now. I shall briefly return to the last topic that we were discussing when we ended our last class. That was on using radioactivity to measure time, radiometric dating. So there was some confusion, I thought, about this point at the top, radiocarbon. How is radiocarbon produced? So I checked, no, everything is all right. Everything has been written correctly. So let me just briefly touch upon one or two points from that. Cosmic rays enter the Earth's atmosphere and collide with the nuclei of atoms to produce neutrons. So it collides with the atoms or molecules in the atmosphere, in the upper atmosphere, and then the collision process produces neutrons. So these neutrons then in turn react with normal nitrogen that is found in the atmosphere. Remember that the uh, Earth's atmosphere, the air that we have on our planet is about 80% nitrogen. So these neutrons that are produced by the collision of cosmic rays with the upper atmospheric particles, they produce neutrons. Then these neutrons react with 14 nitrogen to produce radiocarbon 14C. And then these radiocarbons undergo a beta decay, and that happens on a time scale of roughly 5,600 years. Okay, so this point I'm clarifying again. So everything that is written over here is correct. Broadly, we don't have to worry too much about how cosmic rays produce the neutrons. The more important thing for us is the production of radiocarbon and then their subsequent decay. The decay is more important. And then I mentioned to you that all of life form is based on carbon-based life form. And so this radiocarbon is ingested through photosynthesis in plants, and then they get lodged in plant matter, that is wood, and leaves, wood, whatever. Then animals eat them, and then gradually, once herbivorous animals eat them, then it enters the animal food chain. Later, carnivores eat these things. So all of us, all animals, including us, have a little bit of radiocarbon in our bodies. Okay. Now, there was this one last point which I finished, we ended upon. That was that this is the equation that you shall use to find the time scale. T naught is the initial time and X naught is the initial amount of dead wood. So you're trying to understand I mean, this is an equation of general applicability. This equation is one of general applicability. Any time scale measurement that is to be done using radioactivity would involve this equation. But the problem is that one really doesn't know how much of the initial amount was present when it all started. So you just take a small sample out of a certain amount or a certain, dead charcoal or whatever. So best is that since rate, this x naught was the initial state. Since rate is proportional to the state, we use this equation. So x naught by x is also equal to x naught at initial time t naught divided by x dot at initial time t naught divided by x dot at present time. So x dot at present time from a dead charcoal sample could be measured without too much difficulty because that can be done with the help of a Geiger counter. A Geiger counter is a measuring device which measures radioactivity. So an x dot at T naught, although we do not know what was x dot, but we can find the equivalent. This is the initial amount of matter, so fresh wood, let us say. We can immediately find the radiocarbon activity of fresh wood by applying the Geiger counter to live trees or plants. So this number could be found indirectly by exploiting the fact that rate here is proportional to the state, right? So once we have these two numbers, then knowing the half-life of the radioactive sample that we are using, we should be able to measure the time that has elapsed. So that is the point that has been written over here. X naught is difficult to estimate. It is easier to find the decay rates x dot at t naught and x dot at t for dating. I told you how you should be able to find that. And then the last point is that this is something about measurements once again, which I have touched upon many times earlier. Suppose I ask you, let us just worry about length scale. Length, not time, although we are talking about time, but just to give you an example, let us worry about how you measure length. Now I ask you to measure something that is of a millimeter length, right? Then the millimeter length scale, let's say a hair's breadth, hair's breadth is actually much smaller than a millimeter, or whatever, some small object with a millimeter length scale. So I shall have to give you an apparatus whose least count will be of comparable order. I so it is that you can't measure an atom with a millimeter. I mean, so if it's something, if the object that you're measuring is over the millimeter length scale, then you should use a ruler, a standard ruler with graduations of millimeter, centimeter, etc. Now, if I ask you to measure a bacteria or a virus, that you can't measure with your normal ruler. Then at the other end, if I ask you to measure the size of the solar system or the galaxy, or even planet Earth, or even the size of your country, so you can't do that with a ruler. It is impracticable. So the point is that whatever you are measuring, whatever scale you are measuring, your measuring device should be operating with a least count on a comparable scale. And so it is with this time measuring radioactive dating or radiometric dating experiment. So this radiometric dating also follows the same principle. Why? Because you use radiocarbon dating to find the age of civilizations, and civilizations will enter wood, use wood, right, from charcoal or wood structures of ancient civilization. Charcoal as in the outcome of burning a fire, lighting a fire. So civilization has been there on record for something like 5,000 years. So it is fortunate for us that radiocarbon also has got a lifetime, half-life of a comparable order. And radiocarbon can be found in wood material, so charcoal or wood structures, which would be dead, used in ancient civilizations. So basically, radiocarbon can be used. You can't use, let us say, uranium-238 to measure the lifetime of a civilization. Why not? Because the time scale of uranium-238 decay is 4.5 to 10 raised to 9 years, 4.5 billion years. So if something has been in existence for not more than 5,000 years, and you are using a radioactive material whose half-life is 4.5 billion years, then over a time scale of 5,000 years, practically nothing would change for change in terms of measurements. I mean, whatever you start with will remain practically the same after 5,000 years. So uranium wouldn't change in amount at all. And then you can't do the other way around. Suppose you want to study the Earth's geological processes, the time scale of the Earth's geological processes, then you should not use radioactive carbon either, because geological processes happen on a time scale of millions and billions of years. For instance, the dinosaurs, they died through because of various geological processes. They became extinct. Now they became extinct 65 million years ago. 65 million years. So if you want to study the aging of those geological strata in the Earth's interior, then you can't be using radioactive carbon, because this is in You start with a certain amount of radioactive carbon, it will be reduced to half of what it was over 5,500 years. And then again, it will be reduced again to half of what it was over another 5,500 years. So in about something like 1 lakh years or so, all of it will be practically zero. So you will have nothing to measure, really. So I mean, if something goes down to the amount of practically zero over a time scale of 50,000 years or 1 lakh years, now what change can you expect any further to happen on a time scale of million or billions of years? So you then will have to use something on a longer with a longer half-life. So that is why for geological dating, nuclei with longer half-life are used. The example longer of a long half-life is the uranium-238, which is 4.5 billion years. Anyway, so I hope I have been able to establish these ideas that whatever time and all these things you're trying to measure, your measuring apparatus should also be operating on a same time scale, right? Um, for instance, your pulse beat is on the time scale of 1 second. So if you want to find the time scale of electron transfer in an atom, which happens on a time scale of nanosecond, your pulse beat is not the right kind of clock to use. So just to give you an example. So measuring device and the physical phenomena must operate on the same scale of time or length, whatever, for you to have an understanding. Anyway, so next topic that we shall move on is it's very simple thing, QRC circuit. As I said, we shall discuss various phenomena using our knowledge of autonomous equations, which is dx dt is some function of x, right? Here the function of x was minus lambda x for radioactivity, with which we have seen a practical application, namely radiometric dating. Now we shall look at another such phenomenon uh, where this autonomous equations can be applied, namely a very simple electrical example of a QRC circuit. Let us see what is this whole business about. Here is a simple circuit diagram, which you should understand what it is. There's a switch, there's a source, battery or whatever that creates a potential difference across this over this entire circuit. There's a resistor and there's a capacitor. Now, if you close the switch, then current will flow because the battery will then drive a current by creating a potential difference. So there will be a potential drop at the resistor. That should be familiar to you. The potential drop at the resistor will be V is equal to IR, I being the current, R being the resistance of the resistor. And then here in a capacitor, you will have a charge buildup. Now, what will be the potential drop at the capacitor across the capacitor plates? Now, charge building up in a capacitor is C, of course, is capacitance. It's a constant value. Both R, V naught, and C are constant quantities for this system. And so, as charge will be building up, so there will be a potential drop across the capacitor plates as well. And so that potential drop Q is equal to Vc. So the potential drop will be Q by C. Okay. So over the full circuit, you have a voltage drop here and you have a voltage drop here. And the two of these things will add up to the total voltage potential difference across the circuit, which is V naught. V naught is equal to IR plus QC. So here and here. This is the equation. Now, what is current? Current is, so if you look at it, V naught is constant, C is constant, R is constant. The only two things that change are Q and I. So what about I itself? I is equal to dq dt, time rate flow of charge. So basically then I can write this thing as R into dq dt is equal to V naught minus Q by C. And then I divide throughout by the resistance R, and I get dq dt is equal to V naught by R minus Q by RC. So which is in the form, if you look at it, V naught by R is a constant, Q is a variable here, and dq dt is the time rate change of Q here, and RC is again a constant. So dx dt will be so this is in the form of dx dt is equal to A minus Bx. I hope you are familiar with this equation. We have discussed this thing at great length. And so A is equal to, or A is the equivalent of V naught by R, and B is the equivalent of 1 upon RC. What is the solution of this equation? X is equal to, you just refer to the notes that we have discussed in the mathematics theory class. X will be equal to x naught into 1 minus e raised to minus bt. What is x naught? X naught is a by b. So we are just doing that. Q is equal to x naught, which is equal to a by b, which is v naught by r, divided by 1 by rc. And this 1 minus e raised to minus bt. B is equal to 1 by rc, minus t by rc. And so this 1 by r and this 1 by r will cancel, and you'll just have v naught into c. So v naught into c is dimensionally q, except that this is the maximum possible attainable charge. So basically what is happening? Charge is building up in the capacitor, right? So what equation does it follow as it is building up in time? The equation of charge buildup in a capacitor follows this equation, Q naught being the maximum charge buildup value that you can have in the capacitor, and that is equal to V naught into C. So initially there will be a linear growth, and then it will slowly saturate towards this thing. And B is equal to 1 upon RC. So what is the time scale of this problem? The natural time scale of this problem, once again refer to the note, will be 1 upon B. So you can see that this thing, this whole thing will be dimensionless. Minus T by RC will be a dimensionless quantity. And I told you many times earlier, exponential, all these transcendental functions in general, exponential, log, sine, cos, etc., very commonly used transcendental functions. Transcendental functions are functions that can be represented by an infinite series. The word transcend means going beyond, right? So, I mean, whatever large order you write, there will be another large order beyond it. So if it's an infinite series, that is why the name is well chosen and self-suggestive. So it's a transcendent, any function that is represented by an infinite series is a transcendental function. And a transcendental function must have a dimensionless argument. So if t has the dimension of time, then RC must also have the dimension of time. And so time scale, natural time scale in this system is R into C. So before that you have a linear growth, after that you have saturation, slow saturation towards the upper limit of Q naught, which is the limiting value. So you can see here is a very simple laboratory experiment. I told you we shall be talking about equations where we use dx dt, equations of the form dx dt is equal to fx. So the first equation that we used was of radioactivity, and the radioactivity is x dot is equal to minus lambda x. Fx is a linear function, very simple linear function, minus lambda x. And here x dot is equal to a minus bx. Both are linear functions. Okay. Now let us look at another such system, namely, so we shall just initially discuss some very basic physical systems where you can apply your knowledge of what you have studied in the mathematical theory as well as your basic physics concepts where can be applied here. And you should be able to, in the lab, next week onwards, I shall give you some simple problems to work on using these physical work in these physical systems using simple equations of the form x dot equal to fx, right? So let us see. Here we are. We are talking about viscoelasticity. Let us first try to understand the meaning of the term viscoelasticity. What is this viscoelasticity business? It is viscosity plus elasticity. In order to understand that, we shall have to look at physical contexts, the physical contexts where the idea of viscosity and elasticity apply. The ideas of viscosity and elasticity apply. Let us see. See, usually in your common experience, that there are matter could be seen to have three broad phases, three general phases. First is solid phase, or solid state, if you like. Second is the liquid state, and the third is the gaseous state or gas phase. Now, elasticity is associated with the solid phase. Let me just give you a simple example. You take a steel ruler, right, 1 foot ruler. You're familiar with this sort of a thing. You take a steel ruler or a spoon or whatever, something, some metallic thing, elongated, and you bend it and then you release it. Once you bend it and thereafter release it, so if you bend it, it'll of course give way under the force that you have applied and be bent. And then as soon as you release it, your steel ruler, as soon as you release it, it will spring back into its original shape, whatever it was earlier. Unless, of course, you badly twist or turn it, then it's a different matter altogether. So this tendency, springing back to regain its original shape, whatever it was before you applied your force to bend it, is due to a property known as elasticity. What is it? Loosely speaking, it is the property of solid objects to retain, it is the tendency or property of solid objects to retain their given shape, a solid crystalline object. By the way, when I say a solid object, I'm referring to an object where you have got properly defined structure within the system. In a metal, for instance, you've got a properly ordered structure. Ice, for instance, has got a properly ordered structure. But wood, although it looks solid, you can get hold of a log or a stick or whatever, all made of wood. But wood does not have a well-defined crystalline structure. Hence, such a material is known as amorphous. Amorphous means without form. So, but solid material will have some. Usually, I'm talking about crystalline material, ice or metals. These things, they have a well-defined order in the way the atoms inside the material are arranged. Therefore, so when we talk about elasticity, we should be referring to such things. For instance, if you bend wood and then release it, it's unlikely, not, usually not likely, although you can do such things with cane and all that, whatever. But in metal, the property is more, better displayed. Okay. So let us now look at this elastic property with an example. Here is a wire of a certain crosser, a thin copper wire, whatever you want to look at it. So you have a thin copper wire, and this copper wire has got an area of cross section A, copper, steel, whatever, but metallic wire. It is the area of cross section A and a length L naught. And across you are stretching the wire, you're pulling the wire, you're holding one end of the wire with your hand and the other end you're pulling. So you're applying some force. So the wire will get extended a little, it will be strained a little. So let us now familiarize ourselves with definitions. Stress is defined as force per area over which the force is being applied. So if you're pulling the wire, force is being applied longitudinally along the length of the wire. So force is acting this way, and stress is defined as the force applied on unit area of cross section of the wire, force per area. So stress is equal to force upon area, and stress is also proportional to strain. What is strain? Strain is the elongation over the original length. So if the elongation is delta L, strain will be defined as delta L divided by L naught. In a supplementary set of notes, corrections, I just elaborated on this point a little. I'll get back to that, but this shouldn't be too difficult. So suppose your wire has got 1 meter length, and you have pulled the wire so that it gets extended a little by, let's say, 1 millimeter. Right, 1 millimeter extension, it has happened. Wire being metallic, made of metals, can't be pulled and stretched so easily, by the way. But let's say you have managed to extend the wire by 1 millimeter. So strain will be 1 millimeter elongation divided by the original length of 1 meter. So 1 millimeter is 10 raised to minus 3 meter divided by 1 meter. So strain will just be a dimensionless quantity of 10 raised to minus 3 in this simple numerical example that I have just discussed. Okay, so stress is proportional to the strain. so stress is proportional to sigma is the stress is proportional to epsilon. So that is what it is. And the proportional constant is known as Young's modulus, Y as in the name of Young, Thomas Young, as in Young's experiment of interference, which I think you would have studied at school. It's there in, I think it's there in the CBSE syllabus, interference, diffraction, all these things of optics, that is. So sigma is equal to, is proportional to epsilon, and the proportional constant is written as y is Young's modulus, which is an elastic property of a solid with a defined structure. Right, a solid will have a defined structure. When I say solid, once again, take care to note that I'm usually tacitly referring to crystalline solids, not something like wood or any such thing. Right. So you have an elastic property associated with a solid that is captured numerically or captured in measurable terms by a constant known as the Young's modulus. Okay. Next, we are talking viscoelasticity, which is viscosity plus elasticity, right? So the next thing that we talk about is viscous property. Now, be careful in noting that all that we have discussed so far about elasticity, our standard reference point was solid materials, right? Was solid materials. So we referred to some kind of a crystalline solid where elasticity applies very well. For instance, ice is also a crystalline solid of H2O, right? Water is the common name given to the liquid phase of ice. Ice is H2O solidified, and the molecules of H2O, once ice has been formed, they get arrayed in a very nice, neat structure, a very well-defined structure, ice crystals. Anyway, but viscosity is a property that you associate with liquid. How are we suddenly bringing them together in a common platform known as viscoelasticity? We shall discuss this thing soon. Let us see. So first, let us try to understand what is viscosity. Here is a little diagram. Let us see. Z is the vertical axis, X is the horizontal axis. So, I mean, there's also a Y axis. X cross Y will give you Z. So Y is probably heading into the plane of the paper, but that is not important. You are just observing a phenomenon in which liquid water is flowing. Suppose you are at your dining table, and by mistake you have turned over your glass of water, and so immediately the water will start flowing out. So this is the water flowing out. So now let us try to see. You are observing it at a cross section. This is the height above the table, and this is the flow of water streamlines. I'll come to that word, streamline, shortly. So there is a viscous drag. What is a viscous drag? Fluid friction between adjacent layers of a flowing liquid. Let us try to understand what is this. Friction, you know, what is friction in the case of solid material? This is once again something that you study at school. In the case of solid material, friction refers to the resistance to motion offered by a resistance to motion, adjacent motion, uh, that two surfaces experience. Just simple example. We have just come. We are coming out of the winter season. In the winter season, very cold. If you go out on very cold mornings, your palms become very cold, right? And so, to warm your hands, what do? You rub your two palms against each other. Two flat surfaces you create with your two palms by stretching your palms out, and then you bring these two surfaces of your two palms in contact with each other, and you rub. And as you rub, you feel a warmth slowly generated between your two palms. Now, what is this all about? So this is because there is friction. So between the two palms, one palm is trying to oppose the motion of the other uh, as it is adjacent next to it. So two palms are forming adjacent layers of, let's say, skin. Okay, so something similar happens in the case of viscosity. So here you have layers and layers of water, plain layers. Since you're looking at a cross section, I've drawn the layer with a line. So this is just like looking at a plane edge on. So this is a plane actually coming out of the paper, going towards your eyes and going into the paper on the other side, whatever. But if you're looking at a plain edge on, it will look like a thin line. So this is a layer of water, this is a layer of water, this is a layer of water. As you can see, that layers that are above are flowing faster than layers that are below. And the slowest moving layer is the one that is just sticking to the tabletop. You have, by mistake, overturned a glass of water, and the water is flowing out. So the higher layers are moving faster than the bottom lower layers, and the slowest moving layer is the bottommost layer. Now, just like two palms, if you rub them against each other, they offer friction to the relative motion between the two surfaces. So it is that fluid also has a friction. Fluid friction is loosely viscosity, viscous property. So what is this? That there is a viscous drag, fluid friction between adjacent layers. So this is one layer, this is one layer. Of course, the reality is far more complicated, but I'm just giving a simple representation. So you've got two adjacent layers. And so these two adjacent layers, this one is flowing faster than this. So the bottom layer will try to pull down the top layer, and the top layer will try to drag the bottom layer ahead with it. So there is a contest between the two of them. And so this contest is arising because of an inherent friction property in liquids, although friction is something that we associate with solid materials like and I just gave you the example of rubbing two palms against each other. You can take the example of rubbing or striking flint against some hard surface. So the friction is so strong that it will give rise to sparks. So like that. So here it is something similar, but this friction that we are talking about is to be qualified by the word fluid. It is fluid friction, viscous drag. So you have friction, some sort of friction, fluid friction between two adjacent layers. Now let us see what is the force. So when you offer resistance, you have to apply force. Suppose somebody is driving a car towards you, let's say very slowly. In all these strength demonstrations, what people do, somebody is trying to drive a car slowly and someone else tries to stop it by pushing against it. So whenever you are applying a force to resist something, whenever you're trying to resist something, you are applying a force. So what is the force that is being applied? Let us now see what that is. So you have a layer here and you have a layer here, so in contact with each other, although this gap doesn't suggest that there is contact between two layers, but I've drawn this for us for simplicity of understanding. So you have two such layers in contact with each other, and the area of contact is capital A. So then the drag force between these two layers, mind you, the bottom layer is trying to pull the top layer back, and the top layer is trying to pull the bottom layer forward, right? So that's how it is. It's just that the top layer moves faster and the bottom layer slower. So whatever happens, so what is the drag force that you have? The drag force is proportional to the area of contact. Of course, that is naturally to be understood. Larger the area of contact, greater will be the resistance, right? If there is no contact, then there will be no resistance. Very simple thing. And it is also proportional. So the force that you have is proportional to the area of contact and also proportional to the vertical velocity gradient. What is that? Let us now see. Here, the velocity is much higher compared to here. And here the velocity is higher compared to here. So, sorry, so velocity is changing as you're going along the z-axis. Higher and higher values of velocity for higher and higher, larger and larger values of z. Velocity, of course, is in the right direction, going from left to right. That is velocity. But the velocity gradient that you measure with respect to z is changing along the vertical direction. You will see that it has got a gradient along the vertical direction in the sense that for a certain value of z, you'll get a value of velocity. For a higher value of z, you'll get a higher value of velocity. So you can see that it has got a positive gradient. So the drag force between any two adjacent layers will be proportional to the area of contact between the two layers and also to the velocity gradient that is there. Local velocity. What is the velocity gradient over here will determine the drag force between this layer and the layer above and also the layer below. So that is how we write it. And viscous stress, just like this stress here in elasticity, still follows the same definition. It is force upon area. Stress is force upon area. So viscous stress will be this force upon area. So force upon area will be proportional to dV dz. So I'm still writing sigma for viscous stress, dVz dz. And so sigma will be equal to a dV dz into a proportional constant eta, where eta is a coefficient of viscosity. For instance, if eta has got very low value, then you will say that there is no viscous stress. I mean, very small viscous stress. If the eta has got a high value, you will say that the liquid is viscous. For instance, take the simple example of water. Water, if you turn over the table, water or milk, they will all flow out very quickly, right? Milk is almost 80% water, so they will all flow out very quickly. Whereas if you turn over a pot of honey on the tabletop, honey will not flow out that rapidly as water or milk, right? Why so? Because honey has got a higher coefficient of viscosity. So adjacent layers in honey will not move as fast as adjacent layers of milk or water. So that is the reason. Certain liquids flow slowly, certain liquids flow much more rapidly. It is dependent on the value of the viscous coefficient or coefficient of viscosity eta. Okay, we shall now do a little bit of mathematical trick with this. Some little trick that we apply using chain rule. So what we do is that sigma is equal to eta dv dz. And what is dv dz? V is the velocity in the horizontal direction. So v is equal to dx dt, as has been drawn here. So we write this thing as eta, sigma is equal to eta ddz of dx dt. Right. If you have this thing, then next task is you just exchange these two dz and dt in the denominator. Earlier you had dt first and dz after that, but now you are interchanging them. You have dz first and dt after that. So that you can do. Very simple. Now we shall look at what is dx dz. Here's a simple diagram. Z is the vertical axis, x is the horizontal axis. So dz is a small displacement along the vertical axis and dx is a small displacement along the horizontal axis, right? And so dx by dz, dx gets stretched in from left to right and dz gets stretched from bottom to top, right? That is how it happens. And the angle that you have over here, if you say epsilon, then by this definition, by trigonometric definition, epsilon being the strain, I'll talk about strain very soon. Epsilon being strain, we write tan of epsilon. You see that tan of epsilon will be equal to dx by dz. Now, why are we calling this thing strain or shear strain? Let us see. What is strain? Strain is basically a form of, is a kind of deformation. Here you had longitudinal strain, a little elongation of the wire over its original length L naught. So strain will be delta L, the elongation, divided by L naught. That is strain here. Here, you are not having a longitudinal strain as in the case of the wire. Here you are having some kind of a shear strain. What do I mean by that? That you see the top layer is trying to move forward and the bottom layer would not allow it. And the bottom layer is trying to stay back, but the top layer would not allow it. So the top layer is trying to pull the bottom layer forward and the bottom layer is trying to pull the top layer back. The top layer will be trying to push the bottom layer forward. And so as a result, there will be this kind of a curvature that will form. A small element of length, dz and dx, the curvature could be matched as a straight line. And so this little straight line that you have is actually a part of this curved dotted line, right? So that is drawn over here. So it is as if that because of this differential motion between two adjacent layers, differential motion meaning that two adjacent layers are traveling with different velocities. Because of the differential motion of the two adjacent layers, this thing is getting pulled out of shape, right? Pulled out of shape. So it really, ideally, this point, this point, this point, this point, and this point, all five of them should have been along a vertical line and they should have marched forward in proper discipline. But rather than such a thing happening, the bottommost layer, this black dot, is moving the slowest, and the top points, the higher points are moving much faster. So that's the strain that is happening. So epsilon is the angle that captures the strain, right? It's shear strain. Epsilon captures that strain. If epsilon were to be zero, then there would be no strain. I said that all of these things, instead of this curved dotted line, you would have had a vertical dotted line, and they would have all marched in proper discipline in tandem, like soldiers marching on Republic Day. So now we shall look at this thing. As I said, tan epsilon is equal to dx dz. But for small values where this shear strain is not very large, one doesn't see any such thing happening. Maybe it's happening on a very small scale, but you don't see a situation whereby a very giant column of water flows like this thing, right? So that the bottom layer is almost not moving and the top layer is coming like a giant wall and falling over you. It's that sort of a thing doesn't happen usually. I'm saying usually, but it does happen in the case of ocean waves and all that. But that's a different, I mean, I don't want to get into that complicated discussion. Let's just say that this epsilon is small. So epsilon being small will mean tan of epsilon can be approximated to be epsilon. So epsilon is approximately dx dz. Right. And so in this formula, sigma is equal to eta d dt, dx dz is dx dz is substituted with epsilon, and you have got sigma is equal to eta d dt of epsilon. Now you combine, so this is the viscous stress as has been created, and this is the longitudinal elastic stress, right, as has been created. This pertains to elasticity, and this pertains to viscosity, which is liquid, whereas this is solid. Now you can ask me a very important question. Why am I going to combine? Combining sigma is equal to ye to account for both elasticity and viscosity. We get sigma, total stress, will be the elastic stress plus the viscous stress, which is the equation of viscoelasticity for a fixed stress. Stress is a force, stress is just loosely thought of, is the force that is applied. So somebody applies a certain force, fixed force, and then it's to be divided by the area, etc., whatever it is. So you can ask me an important question. How is it that you just said elasticity pertains to solids and viscosity pertains to liquids, and yet you are bringing the two things together? Either you have solid as in ice, or you have liquid as in liquid flowing water. But how can you have both solid and liquid coming together in the same physical frame, physical discussion? So that is the thing, that you have certain materials where both elasticity and viscosity are displayed. Such materials are known as viscoelastic materials. I will give you a simple example. I believe that you've seen road work being done, road repairing. So with the help of road rollers, stone chips are put on the road, and then the stone chips are made to stick to one another by liquid black tar, black liquid tar, right? Now, this black liquid tar is an example of a viscoelastic material. Let us try to see. If you have been observant, you might have seen such things. When the temperature becomes high, the material, so suppose you've got a can full of or a drum full of tar. In the winter months, when the temperature is cold, and typically these things are left outside on the roads, right? So in the winter months, when the temperature is cold, if you turn over the drum, nothing will flow out, right? Because it will be more solid than liquid, but nothing will flow out is on a time scale of maybe 1 or 2 minutes in which you have observed. If you keep the drum turned over for a long enough time, on the time scale of days, then slowly, regardless of what the temperature is, if the temperature is cold, then the movement will be very slow. Slowly, you will see that the tar material is coming out and gathering around the mouth of the drum, mouth of the overturned drum, right? In the summer, when temperatures are higher, this property will be more visible. In the winter, it will behave like it's almost a solid, like a solid. You wouldn't be able to tell on your time scale of observation that it actually has liquid behavior. So that is an example of viscoelastic, a viscoelastic material. It has got features of both a solid material as well as a liquid material. If it has got features of solid material, it will have elasticity captured by Young's modulus, as in here. And if it is like a liquid, then it will have viscosity captured by eta, as in here. So for a fixed stress, you have this thing. So once again, now the next task is that if you look at these things, sigma is a fixed stress, y and eta are the fixed values, parameter values pertaining to the material, y being the elastic parameter value, Young's elasticity, and eta being the viscous parameter value, liquid or fluid parameter value. So that is what it is. Now, Young's modulus pertains to things that have a defined structure. So when you turn over a drum full of tar, it has got a cylindrical structure. It would rather try to maintain its structure, but then slowly, slowly, on the time scale of a week or two, you will see that the material is actually flowing out. So what is the major difference between a solid and a liquid? In the case of a solid and a liquid, the first major difference is that a solid has a defined structure, a liquid doesn't have a defined structure. A liquid assumes the shape of the vessel in which it is put. So if you turn over a glass full of water, the water will flow out. But otherwise, the water will assume the shape of the glass and stay put inside the glass. So that is what it is. Now, let us look at this equation. Epsilon is the strain. That is the one that is changing. And how will it change? Let us see. Uh, Epsilon and t. T is also a variable. So what we do now is that we take y epsilon to one side, so sigma minus y epsilon, and then divide throughout by eta, and we will get d epsilon dt is equal to sigma by eta minus y epsilon by eta. Sigma, eta, and y are fixed quantities of this system. Therefore, this is an equation that is again in your familiar form of dx dt is equal to a minus bx. And the solution of this equation for the initial condition that we have familiarized ourselves with. Remember, in this sort of an equation, as well as in the previous equation here, you can afford to take as an initial condition of at t equal to 0, x is equal to 0. So at t equal to 0, there is no charge build up in this thing, right? So like that. So here also we can do that because when x is equal to 0, dx dt will not be equal to 0 because of this a, non-zero a. But in that case, you can make x is equal to 0 at t equal to 0, but dx dt non-zero will make x grow, non-zero and positive. Assumption is, of course, that a and b are positive quantities. Here, all of them are positive quantities, q, eta, y. Similarly, here also, all of these things are positive quantities, v naught, capacitance, resistance. Nobody here may claim that he or she has used negative resistance in class 12 physics. Okay, A is equal to sigma by eta and B is equal to y by eta. Y by eta. Right, so there's a slight error over here. It should be y by eta. So, yeah. So, yes. So now let's see what we will do is that we will write the solution of this equation when t is equal to 0, epsilon is equal to 0. So the solution will be a by b. A by b will be sigma by y. The two by etas will cancel. 1 minus e raised to minus bt. Minus b will be y by eta. Y by eta is minus bt. So the natural time scale will be 1 upon b, which is eta by y. So the natural time scale of this system is 1 upon b, meaning that you will see on a time scale of eta by y, in the early stages, you will see the liquid flowing out, and this deformation will be more prominent, and the liquid will flow out. And then after that, it will saturate to a limiting value of sigma by y. Now, this formula, sigma is equal to y epsilon plus eta d dt of epsilon, was was used by Kelvin. Kelvin, as in the person after whom the temperature scale, the absolute temperature scale, is named. the geological problem of solid rocks flowing out under the weight of earth matter above it. You see, the Earth is mostly the Earth is a silicon-based planet, silica-based planet, right? It's an interesting point. You should make a note of what I'm saying, just for general knowledge, that life is mostly carbon-based. All of you are predominantly carbon. Then there will be other. All these organic molecules are carbon-based. Like in organic chemistry, you study all the features of carbon, all of these things, because carbon is a tetravalent element, right? But the Earth is dominantly silicon-based. What is the common feature between carbon and silicon? Both are tetravalent elements in the same column of the chemical periodic table. So life, biology is carbon-based, and Earth, geology, is silicon based, right? So for all you know, one day you may all go to, if you do very well in your professional careers as ICT engineers, you may go to the famous Silicon Valley in California. So as you can see, but most of the earth rock matter is silica based rock matter. So they form, I mean, they are solid rocks. Now, in the deep interior of the Earth, the solid rocks experience huge pressures because of the weight of all the Earth matter above it. And under pressure, we follow this point carefully. Although these things are very solid, we use the term rock solid, right? Although, of course, rocks are solid, but the thing is that the pressure is so great, that is to say, this sigma, the stress is so great due to the weight of all the Earth matter above it, that these rocks actually deform and start flowing out. Like in the way, let's say that you have butter in a fridge, right? So, fridge creates a very cold environment, and in that environment, if you keep butter, butter will freeze and become solid tight. Now, if you press the butter with your fingers, even then the butter will get squeezed under the pressure of your fingers and start flowing out. Similarly with wax, as in candles. Although they look solid, but if you apply enough pressure, it will start flowing out. So although they look solid, they have a defined shape and all those things. Uh, Under stress, their liquid kind of behavior or fluid kind of behavior is becomes apparent. So that is what it is. That's a solid rock will flow out under this large stress of that's being applied. Maxwell, your old friend from electromagnetic theory, gave viscosity for these kind of systems, these kind of material. He gave the name fugitive elasticity. It is as if that these things, although we experience them as liquid, uh, but under certain conditions, they behave like as if they are solid, right? So Maxwell gave the viscosity of such materials the name fugitive elasticity. Fugitive elasticity meaning hidden elasticity. Fugitive meaning somebody who has taken refuge, somebody is hiding, right? So fugitive elasticity, so it is viscosity all right, but it is like the thing tends to retain its shape unless a good deal of stress is applied. So you call such things a viscoelastic system. They have solid properties as well as liquid properties. So that's one example of solid rock flowing out under the weight of the earth. So usually you would think that when you want to make things flow out, you'll have to apply temperature, high temperature, I mean, heat it up and take it to a very high temperature. Thereafter, it will melt and flow. But even very high pressure can make solid material flow. So this is one such example. Solid rocks will flow out under the high pressure of all the earth matter piled up above it. So this equation of viscoelasticity was established by Kelvin, and it's a serious thing for students of geology or geophysics, where these things are typically applied, this time scale and all these things. So these things matter in the context of geological dating and all that. Anyway, So I have finished the discussion of some simple linear systems. What are the linear systems we have discussed so far? X dot equal to minus lambda x, as in radioactivity, QRC circuit, that is also dx dt, or x dot is equal to a minus bx, and also viscoelasticity, where you have this thing, x dot equal to a minus bx. I shall just briefly go to a set of correction notes. There's also a correction to be done here, y by eta. I'll do that correction. So I'll just briefly go to a set of corrections or additional points to make. I told you about this thing. Epsilon is the elongation trace, elongation over the original length L naught. So I'll just discuss that a little. Just a minute. Okay. I hope you can see this thing. If not, you can immediately let me know by interrupting verbally. So here in the top part, this is corrections to physical systems notes. I've just added some extra discussion. You have this was just in the page 5 of the physical systems notes. As I told you that your course material will be broadly divided into 3 categories of topics, subjects: mathematical theory, physics theory, mathematics theory, and physical systems. So in page 5, you have this thing, L naught is the original length, F is being applied across the area of cross section, and as a result, this wire will get stretched and you'll have an elongation of delta L. L naught is the original length. So the strain epsilon will be equal to delta L by L naught. And thereafter, sigma is proportional to epsilon, and sigma is equal to y into epsilon, where y is Young's modulus, the constant that I discussed. Anyway, so this is, so I shall now move on to another application of an equation of the form x dot equal to a minus bx. That is in liquids. So we have talked about radioactive problems. We have talked about this kind of a system, QRC system. We talked about a viscoelastic system. Now we shall talk about a proper liquid system. Let us see how. Just a minute. Sorry, just a minute. I hope all of you can see the new presentation. Please just confirm once again. Hello? Hello, can you please confirm that you can see the new presentation?
Yes, sir. It's visible.
Yes, thank you. Thank you very much. So here, now we shall take up another problem involving liquids. It's a problem of an object falling through a long liquid column. So you have an object falling through a long liquid column, a solid object, let's say spherical. So this black dot, this is the column of liquid, right? A tube or something containing water, and you are dropping some spherical object, let us say, through that long liquid column. So when an object falls through a long liquid column, 3 forces act on it. What are they? Let us now slowly analyze the 3 forces. First of all, as soon as you release an object in a liquid, it will start going down. What makes it go down? There has to be a force acting on it to make it go down. It wasn't going down earlier. So the force is gravity, which you loosely call weight. So that is m into g, mass into acceleration due to gravity. So that is the force with which this object is going down. The second is that there is a resistance to this downward motion. What is causing that resistance? There are 2 sources of resistance to this downward motion, 2 causes of resistance to this downward motion. One is buoyancy. And what is buoyancy? It is something that you would have studied in your school physics. Upthrust is equal to weight of liquid displaced, right? As has been mentioned over here. Upthrust is weight of liquid displaced. Just a minute. There has to be a bracket over here, right? So this is the weight of liquid displaced. where so if you put any object in water, just you can go by your own experience. If you have ever taken a bath in a pool or a pond, wherever, as soon as you get into the water, you will see that you will feel less weighty in the water, right? So it's as if you have lost some weight. I mean, you're not feeling as heavy as you would do. Why is that happening? Because anything that enters water experiences force that resists the entry. And what is this force? This force is the upthrust. Thrust as in force, up meaning upwards, upthrust. And how is that understood? Weight of liquid displaced. So suppose you have this object whose volume is capital V, right? This scripted V, volume of the object. Then the upthrust is equal to the weight. And don't forget, weight is a force, right? Weight is a force, as in gravity. But here the upthrust will be the weight of the liquid displaced, meaning that as soon as this object has entered the liquid, it has displaced some liquid material and occupied a little space that earlier belonged to the liquid. So that liquid will now have to go somewhere wherever it is got displaced, and it will not be too happy about being displaced, so it will offer a resistance. So what is that resistance force? Weight of liquid displaced. How will you find weight of liquid displaced? First, you will have to find the volume of the liquid displaced. What is the volume of the liquid displaced? It is the volume of the object itself. The object has displaced the same amount of volume or same volume of liquid as the object itself has. And then what is the mass of the liquid displaced? The mass of the liquid displaced will be volume into the density of the liquid, rho L. Rho L is the density of the liquid. So rho L into V will be the mass of the liquid displaced. And mass of the liquid displaced multiplied by acceleration due to gravity will give you the weight of the liquid displaced. So two forces so far we are seeing here now. One is this downward force due to gravity, and the second is this upward force due to buoyancy. Okay. Then there is also a third force, which is viscous drag. Water offers viscosity, resistance, viscous drag, in which we are writing it to be proportional to velocity. Whenever something travels through a fluid medium, be it water, be it air, it experiences a resistance. Don't think that this resistance is very small. In fact, higher the velocity, greater is the resistance. I'll give you some examples immediately so that you should be able to see that this is no small business. In fact, it's a very serious business. Every now and then, in one of the previous classes, by the way, I discussed with you why the moon does not have any atmosphere. The moon doesn't have any atmosphere because the atmospheric particles of the moon, there was some atmosphere earlier, long ago. Now, what happened was that the moon surface became so hot that these particles started moving very vigorously. Hotness created high temperature. Under high temperature, the particles started moving very vigorously, so much so that they overcame the required escape velocity to escape the moon's gravity altogether, and they all left. That's all right. As a result, whenever meteors strike the moon, the lunar surface, the surface of the moon, is pockmarked with crater impact sites. You'll see any photo of the moon, you'll see the lunar surface is marked with crater impact. So these crater impacts happen because of external meteors or meteorites that come in to the lunar surface and hit that. So if it's happening on the moon, then it is also happening on the Earth. They are not very far away from each other, just 3 lakh kilometers away, the moon and the Earth, something of that order, 3 lakh kilometers, if I recall all right. Now, constantly the moon is experiencing all these high impacts, but here on the Earth, we don't experience that. Why not? Because the atmosphere is saving us. Such rocks from other parts of the solar system, the asteroid belt or whatever, they come into the Earth's atmosphere, all right. But then these rocks travel at a great speed. And as soon as you travel at a great speed through a fluid medium, the fluid medium will offer resistance against that speed. Just a while ago, I told you use the word rock solid, right? And you also use the phrase thin air, as if to say that air is nothing. So thin, it's nothing. And solid rock is so solid, you say rock solid. But just a while ago, I gave you the example of rock solid, you may say, but under extreme pressures, your rock, solid as it may be, will start flowing, right? And so it is that air, the opposite happens in the case of air. Air, you may call it thin air, but when these external meteorites enter the Earth's atmosphere, they travel at a great speed, that such a great speed that the friction offered by air, thin as it is so great that the rock, the asteroids are rock, right? Rock solid rock. Against air, they are burnt up completely and they just vaporize. They travel at enormous speeds of 40 kilometers, 40,000 kilometers an hour or something like that. The huge speeds with which they enter the Earth's atmosphere. And so 40,000 kilometers, no, I'm sorry, I made a mistake, not 40,000 kilometers, something of the order of 100 kilometers, 40 kilometers or some such thing. But the number is not very important right now. It travels at an enormous speed, and the faster the speed, greater is the resistance offered by the atmosphere. As a result, the friction with the air heats up the rock so much the rock vaporizes, and in no time at all, very rapidly. You also see the same thing with ICBM technology or these space shuttles that go up beyond the Earth's atmosphere and then they have to re-enter. So all of re-entry technology in rockets and missile. Space shuttle, maybe you have heard of the Columbia crash, the space shuttle Columbia, in which the astronaut Kalpana Chawla died. So that happened because I mean there was some issue with the shielding and all that. Something happened, whatever. So you will see when those shuttles make a re-entry, you will be astonished to see how much the front nose of the shuttle starts glowing because of the friction against the Earth's atmosphere. So they become red hot. They start glowing. As a result, I mean, you can immediately realize that those things can't be made of normal metallic substance, material. Those things have to be made of extremely high heat resistant material as well as mechanical impact resistant material. You can just check on YouTube or whatever, re-entry technology or all these ICBM technology, intercontinental ballistic missile. They go beyond the Earth's atmosphere and then re-enter again to go and hit a target on the other side of the planet. So while re-entry, they have to be protected against because they travel at great speeds. So they have to be protected against the friction offered by the Earth's atmosphere. So you can see thin air can offer such great friction to fast moving objects. So if air can do that, then certainly liquid water, which is far denser and more viscous than air, will do that. So that is what it is. So whenever an object falls through a liquid medium, it experiences a friction force against it. This friction force is the viscous drag. Which is written as proportional to the velocity. We all realize that unless the object is moving, there will be no frictional resistance against it. A still object like a hot air balloon or anything doesn't experience friction in the Earth's atmosphere. So the object has to move. Incidentally, aeroplanes and all those things also experience viscous drag, but aeroplanes don't travel so fast that the Earth's atmosphere will start make them glowing or burn them up, right? So yeah. So what happens is that this we know that this viscous drag will have a dependence on the velocity with which the object is traveling through the fluid material, fluid medium. And so we are writing for simplicity this viscous drag to be proportional to the velocity itself, first power of the velocity, where k is the proportional constant and v is the velocity of the falling object. Remember that there are two v's over here. This v is the velocity of the falling object, which is a function of time, and this v, written slightly differently with some script here, two horizontal bars on over here, it's a fixed value, and it's the volume of the object. So don't confuse the one v with the other. And k is the proportional constant of resistance. The resistance will be proportional to the velocity with which the object is falling through this liquid column, and k will be the drag proportional constant. It is known as the drag coefficient. So here there's a little discussion. Friction or viscosity in a liquid, follow this point carefully, friction or viscosity in a liquid opposes motion. It acts only when there is motion, right? Now the drag force due to friction, we are writing it as capital D. The drag force due to friction, we immediately realize must be some function of the velocity with which the object is moving through the fluid or the liquid. Liquid is a fluid whose density does not change. Water density is a fixed property. Oil density is a fixed property, but air is a fluid whose density can change, right? Like closer to the Earth's atmosphere, the density is higher than the density of air above Mount Everest. So the air is thin over there. And so if you want to go on an expedition to the top of Mount Everest, you'll have to carry your oxygen cylinder. Anyway, so when I say fluid, I generally imply both liquid, gas, everything, but liquid is more specific. In this case, we shall be talking about liquids, but occasionally I will also use the word fluid. Now, what is this function d? How can it be written? The simplest form of the function d is a linear function. D is equal to k into v, right? V is being the velocity, and k being, we say that this drag force is proportional to the velocity, and k being the proportional constant. Now, if the object that is falling through the liquid column is a spherical object, although this object doesn't look too good as a sphere, if the object is a spherical object, for a sphere, the drag coefficient, this proportional constant k, is given as 6 pi eta times r, where r is the radius of the sphere and eta is the dynamic viscosity of the liquid. I'll come to this word dynamic later, but just make a note of this word now, dynamic viscosity of the liquid. There are two kinds of viscosities, dynamic viscosity and kinematic viscosity. Kinematic viscosity is simply this eta, dynamic viscosity, divided by the density of the liquid. We shall use that thing later, not now. But this, we are just referring to the dynamic viscosity of the liquid. So you can immediately see that this drag coefficient, it captures how much resistance is being offered to the flow of the object through the liquid. It will of course be, now you follow carefully, it will of course be proportional to the viscosity of the material, but then it also has a dependence on the size of the object, radius of the sphere. R is the radius of the sphere. You can immediately see for yourselves a smaller object with a smaller physical dimension will travel faster than a large object, which may experience, because of its largeness, greater resistance against the liquid. I mean, greater resistance to its motion as it travels through the liquid. So the drag coefficient depends on two things: the viscosity of the liquid as well as on the physical dimensions of the material. For a sphere, radius is the only physical dimension that you have to worry about. Just think of something. I ask you to take a stick, you throw in the water. If you throw the stick into the water, with its pointed surface hitting the water first, the stick will go into the water far more easily. Follow this point carefully. The stick will go into the water far more easily than if you were to throw the same stick flat side on the water surface. In this latter case, it may very well happen that the stick may not even enter the water. It'll just be floating on the water. Why? Because in the latter case, the stick is offering its entire length to the water to resist against. Whereas in the former case, when I ask throw the stick like a javelin, like in javelin throw last year, Neeraj Chopra got the gold medal. How was the javelin being thrown? Pointed the tip first, not flat on. If it were to be thrown flat on the side, it will not go very far. So why is this happening? So why does it travel a greater distance with the tip presented? Because the tip is the point against which the air will be reacting, or the tip of a stick that you're throwing in the water is the point against which the water will be resisting. So if that thing has got a smaller physical dimension, then the resistance will also be small, and the object will have that much easier passage through the fluid medium. So that is what it is. So here it is that this viscous drag, we are writing it as proportional to velocity, where the proportional constant is k for a sphere only, no other thing. Don't apply this thing to a stick or any such thing. Only for a sphere, this k is defined well, 6 pi eta times r. And I have written something at the bottom of the page. The linear function d is equal to kv applies well for small velocity of fall in a liquid. In a liquid, you experience great resistance, therefore your velocity is usually small enough. Small enough. It's not like a meteor traveling through the Earth's atmosphere where the atmosphere is thin and so you can travel faster. You can immediately realize that an aeroplane traveling through air is capable of traveling much faster than a submarine that can travel through water, right? So as you are passing through a liquid of greater density and greater viscosity, your speed will be small. So we are talking about a fluid medium which has got higher density, meaning water, as compared to, let's say, a gas like air, and it has also got a higher viscosity as compared to air. In such case, the velocity will be small and the drag coefficient can be written as a linear function. So this point applies well. Just on this one last point, I shall end. So the force balance equation will be, drag force will be, a force will be mass into acceleration, m ddt of v, that is the weight, downward force, buoyancy, upward force, drag, upward force. Anyway, I shall end here. In the next class, we shall continue the discussion. Also, please just hold on for a minute. I'll have a few things to say. In the next lab, we will have, if you have any outstanding issues regarding your first laboratory report that is to be submitted, you may raise those issues. Remember what I told you, the next lab will be on the 21st, but the first lab report will have to be